interesting enough startup following in your lap can really change the game for that startup.
Well, and I think like Emily...
Just to follow through on what Jared was saying, there's this really interesting kind of counter dynamic that journalists fall into a lot. Shortly after dinosaurs ruled the earth, I was at the Wall Street Journal. And this guy, Don Valentine, came in. He's a big VC in those days. And he said, you guys, every one of you, you find something and it becomes big and you hype it up and then it crashes and you all laugh at it. How could it be so stupid? And then you miss the part where it just kind of finds its way back and stitches itself into society and is like really important. And I've kind of taken that to heart. I'm guilty of it for sure. But it's like, now Theranos is on its knees, but somebody's going to probably figure out spotting proteins for disease tracking. And at that point, we'll be exhausted and we'll go, oh, yeah, whatever. Yeah. And not recognize that something akin to magic has just occurred in the world.
Well, and I think, as Emily said, these are things that are at least attempting to solve problems in our society, problems that we have globally, and we want to see progress. And I think a lot of us are on Team Dawn. We want to see human progress, and that I think sort of comes out sometimes in our writing.
We want to see big progress or like big changes, and no one is excited about like clicking a headline that's like, we are taking a substantial step forward in the right direction on like this front, kind of, we think.
Right.
Yeah.
And so that's not what, and that's just what you're saying.
The kind of incremental improvements that
And then
I was mentioning.
Sorry, go ahead.
I was just going to say, but that's also true of the people who we depend on to write the stories. People don't want to tell a process story. I'm constantly saying to scientists, I want to hear the story about all the failures that went into you coming to this discovery. Because they will publish a paper that took them 10 years to get to this result. And I find it fascinating to hear of all the ups and downs and disappointments and the time that they thought that the cells were going to give them the data they wanted and then they didn't. But individuals, researchers, and companies in particular don't want to talk about that because that's quote-unquote bad press.
I once covered a guy who was building a repository of failures so that other scientists could see, well, that's what didn't work, and I'm trying this thing. And like there was this social network of people like, I'm going to try this. Anybody else ever tried it? And they go, yeah, it failed. This guy in Spain did it. Like, forget it. Doesn't go.
Cool.
It's a
That would be
brilliant
so
idea.
helpful, yeah.
But just the other thing is we're kind of covering delusional people because you have to be. Otherwise, if you really knew the odds on like what a startup is and how often they fail, you wouldn't get out of bed. And the technology they're making has been so transformative that they see shaping the world. They don't just see building a product. Elon Musk gets up last week and says, here's how I'm going to colonize Mars. And everybody's like, okay,
but he might just be the lunatic to do it.
No, he's the far end of a true thing.
Yes, yeah.
Okay, so hashtag delusional tech people. And then I apologize, we're running a little bit short on time for questions, but we have time for a couple of questions. There's a mic up here if anybody has a question for the panelists. And since this is being recorded, if you would ask your questions at the microphone, we'd appreciate it.
Appreciate all of you being here. Now, we've got a variety of panelists here, 2 editors, 2 reporters, and I think Emily mentioned waking up in the morning and wondering, what am I going to cover today? For the reporters, how do you decide what to cover? And for the editors, how do you assign, and how has that changed over the last few years?
Oh, okay, well, I'll start. So I am the morning news editor at Wired as well as the national affairs editor. So, there's always kind of 2 different timelines. There's one of the stories that we're working on a longer time scale, so that we've assigned them. The reporters are working on them for weeks or months, depending on how much research they need to do. And that's something I have in the back of my mind, knowing, when are those going to come in. But in terms of morning assignments and looking at how I decide what other people need to be talking about, social media has really changed this equation for me, and Twitter has become a resource that I rely on almost assuredly too much for this moment, because there are 2 different rubrics. One is, is important enough that people are already talking about it, and it's something that is out there that we need to weigh in on because it's this moment that's happening. Or there's the thing that no one else has discovered yet, and we need to be the first to bring it to their attention. So I look at social media sort of for the former, and to discover the latter, I either depend upon my beat reporters who will bring me pitches, or I have my, proprietary secret places of the internet and world that I am looking, that I would never let anyone see all the tabs that I have, because that's my secret way into trying to get us scoops. So that's me.
I'd agree with, I like the way you frame that. I think for me it's a little different because I'm not a national reporter. I'm focused, solely on Central Indiana. And a lot of times, there's already stories out there that PR folks are pushing and that companies are trying to sell, whether it's a fundraise or a new hire. And that's the stuff that everybody has. And if it is important enough, we are going to go after it and quote unquote weigh in. But we really pride ourselves on trying to find those distinctive stories that nobody is telling. I'll give you an example. It might have been a month or so ago now. Geophedia, which is this hot tech company based out of Chicago, they opened up a office here in Indianapolis last year and said they wanted to hire 300 people here by, I want to say 2018, but you can fact check me on that. And last month, I got a text from a source saying, hey, did you hear about what's going on with Geophedia? And come to find out, they were laying people off. And it's like, okay, if this company just signed a deal with the state to hire this many people and get this much in tax credits, and now they're laying people off, like this is a big deal. So I started calling, and that source was largely unreachable. He was at some conference and couldn't talk, but I started calling folks that used to work at Geophedia, by looking at their LinkedIn pages, and folks that I knew there, and finally got the story. And when I talked to the CEO of it all, this is obviously a story that they're not going to want to push. They're going to want to make these layoffs and keep it moving. But when I talked to him, he was like, how did you find out about this so quickly? Like, I just told the employees. And, I got to give credit to my sources for that one. But, those are the types of stories that I think, to kind of go back to what you were saying earlier about cheerleading, we need to cover the good stories. We need to cover the companies that are hot and that do have a lot of promise. But we also need to, chronicle the ones that are struggling or that fail, to really make sure that we're getting both sides of it.
All right, thanks, Jared. We'll make one more question, and we'll make it quick. Yeah.
Thank you so much for attending. So my question is really on, sometimes when you look at tech news, it's kind of like chasing cool, where everything is cool right there. As a bystander, from Lafayette, Indiana, who have no involvement in terms of what Uber is doing, do you think tech reporters also have responsibility when there's new technology coming out in terms of diffusing it, that it makes sense for people in the, somewhere in Indiana, like for example, like Instagram or Snapchat, when they come up with new features, we just say, hey, there's Snapchat comes up with this really, like the new, call it the
Filters.
No, the
glasses,
spectacles.
yeah, the
yeah,
snap
spectacles,
glasses.
for
Oh, the snap,
example.
yeah.
And then, if you're speaking to a 35-year-old male, he's probably like, well, why should I care about that? So is that also imposed upon you as a reporter to kind of diffuse it? Because sometimes when I read tech news, it's like everything that is new, but less so in terms of, well, how do I make sense about the technologies?
And I think that's a great question. I think it sort of gets to, now to what you were saying earlier about now you have all these different audiences.
Yeah, so the Snapchat news comes out, and then so we have the chunk of the population that uses Snapchat, can't wait for the features to come out, and they're up to date on the latest ones, and before even seeing it, probably understand how they're going to use it. Then we have people that really need a news story that says, like, this is exactly how your physical app is going to change and what you're going to need to touch instead to see new things. And then we're going to need to tell someone, like, okay, guys, there's this thing called Snapchat, and people are on it, and they're talking to each other, but all three are very, very valid storytelling means that need to happen, because the people that are learning that people that don't understand how Snapchat works are missing out on the fact that there is a segment of the population that is communicating with disappearing messages, and the impact that that's going to have down the line is going to be important. So it is really important that we try to figure out how to break down the story for all of these. Yeah, I guess the answer is yep, that's super important, and we're definitely trying to do it all the time.
Yes.
All right. I'm afraid that's all the time we have. Would you join me in thanking our panelists as well as our graphic artists? Thank you all.
Now, another panel from the Purdue University Dawn or Doom Technology Conference with a presentation on the history and future of artificial intelligence.
Let's see. So that's good on my side of things. As long as they're okay with it.
So, are we good? Thanks very much, guys. Well, good morning, ladies and gentlemen, and welcome. It's my pleasure, my great pleasure, to introduce Jennifer Neville to you. Jennifer is an associate professor and Miller Family Chair of Computer Science and Statistics here at Purdue University. Professor Neville, and she's come with us even though her department is enjoying an external review right now, so she's giving up quite a lot to be here, and we appreciate that. Her research interests lie in the development and analysis of relational learning algorithms and the application of those algorithms to real-world tasks. Today she'll present a talk entitled AI Easy versus AI Hard. If you haven't already done so, I'd ask you to please silence your electronic devices, but don't put them away. So as we learned in the last session, 15 years ago, 10 years ago, if you were heads down on your phone during a presentation, that was regarded as a bad thing because you weren't paying attention to the talk. Now it's regarded as a bad thing if you're not on your phone because you're obviously not tweeting about it all the time and communicating, Snapchatting or whatnot. But please do silence your devices. We hope to see you tweeting. The hashtag is Dawn or Doom, and any equivalent posting to Facebook, Instagram, Snapchat, or whatever else, whatever other social means you prefer. Please welcome me, please join me in welcoming Dr. Jennifer Neville.
Okay, thanks, Jerry. Is the mic on? You can hear me okay? Can you hear me now? Yes, good. Okay. Okay, thanks for having me here again at the Dawn or Doom Symposium. This is one of my favorite places to come and talk because I can think at a higher level about talking about what I do to a more general audience than my typical research conferences. So as Jerry said, I have a joint appointment between computer science and statistics. My area of research is machine learning and data mining, and specifically I focus on very complex relational domains where you need to take into account interactions between many entities in order to make efficient predictions, accurate predictions. But today I'm not really going to talk about my own research. I'm going to really try to give you a sense of what's going on in the AI community right now. There's been a lot of interesting breakthroughs over the last few years. There's a lot of excitement about AI, and what I'm going to try to do today is compare and contrast two events that happened earlier this year and talk to you about how to think about what's hard and what's easy in this space given those two occurrences. So really I want to contrast these two recent events that happened earlier in March of this year. So the first major breakthrough that happened was, you can see here, March 15th, was the event where Google's AlphaGo system, computer game playing system that plays Go, won over a professional Go player here, Lee Sedol, and it was a major breakthrough for the community. It was something that, at least when I started in the field of AI, was something that I thought about doing. I taught myself how to play Go and realized I couldn't even learn how to play Go, let alone program a computer to be able to play it. And so this success happened much earlier than people anticipated. And so in the news, this was touted as a major breakthrough and really something that was going to transform what we saw in terms of the successes in AI. However, less than 10 days later, we had another event happen, which you may or may not have heard about in the news. So here, this is March 24th. Microsoft released an AI chatbot onto Twitter. It was called Tay, and it was designed to mimic a young teenage girl that in the AI robot was supposed to interact with millennials and learn how to engage them in conversations on Twitter. And this experiment went horribly wrong, if you didn't see about this in the news. Within 24 hours, this pleasant teenage chatbot turned into a racist, abusive, sexist entity, and Microsoft removed it from the internet within 24 hours of releasing it and apologized profusely about the event. And the important thing here is that they didn't anticipate that this was going to happen. Some of the news that was explained what was going on blamed us as humans for being horrible people on Twitter and turning this cute little chatbot into a horrible mess. What you might not realize is that Microsoft didn't do this unknowingly. They had a similar type of chatbot called Zhao Ice that was being used for 2 years previously very successfully in China, and it was interacting with as many as 40 million people. And so what was really the difference between when they rolled it out in China versus when they rolled something out on the general internet for the general public on Twitter? That's what I'll talk about as I get more into these systems. But the important thing here that I want to contrast from a technological standpoint is that algorithmically in the machine learning space, there's a lot of shared technology between these two systems. So you might think that a computer program that's going to play Go would be very different than a chatbot that is going to interact conversationally with people. But many of the methods underlying these are really the same. And so why was one system a major success and the other a major catastrophe? To understand this, let's go back to the beginning of AI to learn a little bit about the history. So AI has been around for about 60 years now. So it was started as a field in 1956 when John McCarthy, Marvin Minsky, and Claude Shannon proposed to have a 2-month conference, summer conference at Dartmouth to really explore and define what this field should be under the conjecture that all aspects of human intelligence could be encoded in a computer system. Including many aspects of learning. And so when they jump-started the field with this conference, there was a lot of excitement, a lot of effort in many different directions in the field. I'll focus mostly on machine learning because that is my area, but there are also a lot of other areas included in AI that I won't touch on today. So the early work in the field was really inspired a lot by considering how we as humans might be learning and our biological systems. One of the very first machine learning methods is the perceptron, which was invented by Rosenblatt in 1958. And this was inspired by the neural connectivity in the brain. This is a mathematical model that's trying to mimic what they thought happened with neurons, where stimulus would come into the neuron and it would accumulate up until some point, and once it reached a threshold, it would fire a signal, and so they tried to encode this mathematically in this perceptron here. Another early program was Samuel's checkers program that he invented in 1959. It started with game planes, for one of the first game plane systems, where it would formulate this the problem of how to learn and how to play a game as a game tree, where you have to look ahead as to what the outcome of the game might be in order to decide a strategy of what moves to play. And the methods that he used to develop this system really were the precursors to the subfield of machine learning right now that is called reinforcement learning. And in that case, there's not an immediate signal that tells you whether you're right or wrong in terms of what decision you've made, but you have to wait for some amount of time before you get some feedback as to whether you're headed in the right direction or not. And that is certainly the case with games. And finally, the third thing that I want to point out here is that at the same time there was another area of AI that was focused on developing dialogue systems. And so these were the precursors to what now are being used in chatbots. And in these systems there was input from users, and the AI system would have to figure out how to make a response to them. And one of the very first examples of this as a successful system was the ELIZA system, which was invented by Weizenbaum in 1964. And this was really built as a parody, initially, of a Rogerian psychotherapist. And so what would happen, what the system would do is it would interpret some information about what the user had put in through some pattern matching and processing the language that they had inputted, and then picked responses based on certain templates that they had in the system. And if you were going to parody a psychotherapist, you can imagine that a lot of the answers were things like, how do you feel about that? And tell me more, and things like that. And so at first, when Weizenbaum created this system, he really created it to show people how difficult the problem of interacting with humans, an AI system with humans, would be. And he was actually surprised at how many people actually were fooled into believing that this was a human. And so really this was this jump-started work in that field. So let's see. Okay, so how do these basic systems work? I think this has maybe died. Let's consider the checkers scenario. Really, the way that we frame these as learning systems reflects how you might think if you self-reflected about how you yourself learn how to play a game. This is really what we put into our computer algorithms as well. So if you were going to teach somebody how to play checkers, you would tell them about the board. You would tell them about the pieces and what kind of moves they can make, what are the rules of the game, how do you win the game, and so on. And what you would do is you might start off by watching other people play the game to figure out choices of moves, strategies in particular scenarios, or you might play yourself and lose a lot at the beginning, but eventually you would start to understand which moves were good choices and which moves were bad choices, so you can improve your strategy over time. So that's exactly what we do when we put that into an algorithm. And the way that you, I'm sorry, I've messed up my order here. So before I tell you about how the algorithm would do that, let me tell you about the history of the successes that we've had. This is the area where a lot of the general public is very excited to see about what is being achieved by these computer programs. And in 1994, the Chinook checkers program that was developed at the University of Alberta was the first sort of major success at a difficult game where the software was declared a world champion. In 1995, the backgammon playing program, TD Gammon, that was developed in IBM, also got to a grandmaster level. The most surprising thing that happened with TD Gammon is that they found that the moves that the computer program would make were different than what the human players would make. And particularly, they paid opening positions of the backgammon board differently than humans would. And so not only was that surprising, but it eventually was incorporated into human play as well. So the humans learned from the computer program about better strategies than they hadn't thought about before. Some of you may be old enough to remember in 1997, Deep Blue, the program from IBM, also achieved this level with chess when they beat Garry Kasparov. Much of the success from the Deep Blue system was really from architectural, computational improvements that allowed them to do brute force search much faster than we had previously. So that success was very different than the ability to learn with TD Gammon. But then now, recently, we've seen with AlphaGo, those two types of successes have been combined together. And so the system, AlphaGo system that was developed by DeepMind and Google has just now beat this 9-dan professional player in Go, and again had a surprising move that people initially thought was a mistake. It's called Move 37 in Game 2, if you want to look it up. But the professional Go players said no human would ever have made that move. And at the time when they made the move, it was very surprising when the system made the move, but it turned out to have turned the tide of the game and resulted in a loss for the human player. And so, again, they were surprised by what the program ended up doing. So how did the programs do this? They frame this problem of learning how to play a game in a search tree like this. And so what this search tree, this game tree, shows is all possible board configurations. And so this shows you part of a game tree for tic-tac-toe. And up at the top here, you can see that the board is completely empty. And everybody knows the rules of tic-tac-toe. You have X's and O's. X chooses to move somewhere on the board. These three positions represent all possible positions of where X could go, because this in the middle could be here, here, or here, and you'd have the same outcome, and same for the corner position. Okay? So X has to choose where to go, and then after that, at the next level, then O needs to make a choice based on the available spaces still left on the board. And so you can imagine following through this game tree as you have a sequence of choices by the two players would form a branch in this tree all the way to the bottom of the tree, where you'd end up with somebody winning or losing. So this is how we'd frame this as a computational problem. In the problem, in terms of deciding which strategies to play, comes from the fact that when you make this move right here, at the beginning of the game, you have no idea, there's no signal as to whether that's a good move or not, until you get to the end of the game and you figure out whether you've won or lost. So what the algorithms need to do is make choices all the way through the game somehow and get signals as to whether they win, lose, or tie, and then propagate those signals back up in order to change their evaluation of particular moves in order to develop a strategy based on their experience. Okay? So the complexity of this algorithmically comes from the size of this game tree and how easy it is to encode it all and get to the bottom and propagate signals back and forth. So the way that we look at the complexity is to look at the size of the game tree. So how big are these game trees? Well, tic-tac-toe, which is a relatively simple game that you probably don't play anymore unless you have children, because you know that you can't win, and has still 100,000 leaf nodes, on the order of 100,000 leaf nodes, in the bottom of the tree. Okay, and so that's still fairly large. Checkers has 10 to the 31, and then you can see with Go here that this is an order of magnitude larger than checkers, so we have 10 to the 360 here. And so just to give you a sense of how big these numbers are, 10 to the 28 is about the number of atoms in your body, and 10 to the 80 is the number of atoms estimated to be in the entire universe. So these numbers are astronomically big, and if you think about exhaustively searching those game trees, there's really no hope. So just to give you a sense of back-of-the-envelope calculation of how long it would take you to search these trees, let's consider this situation where you could evaluate 1 million board positions every second, okay, which is a lot. If you could do that, maybe our current state of CPUs would be able to do that kind of evaluation, then you would be able to search over the entire tic-tac-toe tree in 1/10 of a second. But when you move on to checkers, it would still take you 10 to the 18 years to fully search that tree. So it's entirely impractical to think about searching these entire trees. So what we need to do to be able to solve these problems is to resort to machine learning. We need to be able to learn whether a particular move in a particular board configuration is a good move without having seen the entire tree. And the way that we're going to do that is through learning. So how does the AlphaGo system work? There are papers and many talks on this, and so I'll try to characterize it very simply here for you. It's really a combination of the ideas that have evolved from these two historical methods here. So deep learning is really a very complicated version of a perceptron. So it's many perceptrons combined together in many layers. And so then learning is much more complicated than it was with a single node here in the middle, but that's where deep learning has grown out of. And so what AlphaGo does is it combines together deep learning and reinforcement learning. So the ideas that come from the checkers playing game, where we have to wait and understand what the reward is going to be after we've won or lost the game, are also combined into their system. And the way they do this is by learning multiple models and combining them together. So in particular, they have two neural networks that they learn with deep learning. And I think I have an animation here. So here is the details from their paper. So one neural network, so you can see there's more complicated networks here, and one neural network is designed to predict the next move given the current state of the board. And so that's a very immediate feedback, because they're not trying to predict whether they're going to win or lose. They're just going to predict the next move. And they trained their model on 30 million positions that they acquired from traces of expert games, so human decisions about which moves to make. And then they learned a second model that's going to predict the likelihood that they're going to win a game given the current state of the board. So this is a much longer range prediction of how good is the situation that they're in at that point. And then they update these two models using reinforcement learning and combine the two together in a complicated Monte Carlo search procedure, so this is only to tell you that it's not a simple approach. It's a very complicated system to solve this problem, but it's really using many of the simple foundational methods that we've built up in the areas of machine learning and AI. So when you think about these game playing systems, the two dimensions of complexity that decide whether the problem is easy or hard depend on here the size of the search space, as we go from small tractable trees here with tic-tac-toe to things that are intractable, like the size of the state space for Go. Things get harder. And also the amount of delay you have until you get some feedback that we can use in the algorithm to do learning. That's also another dimension of complexity. I think I might have forgot to say that one of the factors in these games that impacts the amount of delay you have, it depends on how long the game is. So if your game only requires 10 or 15 moves, then you're going to get feedback after 10 or 15 moves. But if it takes you, on average, 150 moves, then you have to go much further down in the game tree, and your reward is much more delayed. Okay? So now let's contrast this with dialogue systems and what went on with Tay. So in figuring out how to learn how to interact with humans in a dialogue system, really the basic learning procedure is very much the same as what I described for games. But in this case, you need to learn about language and behaviors and interactions with other humans. And so what are the experiences that you're going to have? They're not going to be games with a fixed length of time and a very clear signal of whether you've won or lost in the end. You're going to have conversations with people, and you're going to have subtle feedback about whether they like you and want to continue engaging with you or not. And so this is something that maybe even humans are not all that good at, or we're not uniformly good at, because you hear about these things like social intelligence or emotional intelligence. People who are able to interpret those signals from other people more effectively are valued as having more emotional intelligence. So from those signals, though, once you interpret them, you again should learn from the feedback good strategies of how to engage with people and how to extend and make that engagement more effective. So in terms of the history of dialogue systems, we've also had a number of successes along the way in the AI community. So the history really started with ELIZA, the psychotherapist model that I talked about before. But then in 1995, we had the ALICE system, which was able to convincingly mimic conversational patterns through natural language processing and heuristic pattern matching. This was inspiration for the Spike Jonze movie Her that came out in 2013 and was aired at the Dawn or Doom conference back in 2013. And then you might think that this next one should have gone in the game playing list. In 2011, IBM's Watson system beat top players at Jeopardy! But much of the technology that it was using to play Jeopardy! Are the same types of technologies you need for dialogue systems. So they needed to understand the input from the clue and figure out how to answer the question using a lot of natural language processing and information retrieval techniques. And so although there wasn't the same sort of interaction, it was really a big success for the natural language processing community. So then something you may have heard about in 2014, there was this system called Eugene Goostman, which nominally passed the Turing test. It was a system that was developed by 3 Russians, and in a competition and trying to convince a set of judges that it was human, it was able to convince 33% of the judges that it was human. And so they claim that it passed the Turing test. There's some people that disagree with that claim, because this chatbot here, Eugene Goostman, was developed as a teenage Ukrainian boy, and they used a lot of particular tricks to hide the limitations of its processing system. So because it was a young boy who was from another country, it was very forgiving to not quite understand the language or the questions that people are asking it, and also to be more curious, so to be able to ask more questions and deflect the conversation when they didn't know what was going on. And so this system, while people think maybe it hasn't really passed the Turing test, it did use a lot of techniques like humor and deflection in conversation in a very interesting way that was able to convince these judges that it was human. And so really that should be considered as a achievement in this area. And so then in 2016, I guess this is, you could disagree whether this is a success or not, but when Tay was released by Microsoft, really it was successful. In fact, maybe it was a victim of its own success. So Tay acquired 50,000 followers and tweeted 100,000 times in the first 24 hours that Tay was released. So there was a lot of interest in Tay from many types of groups on the internet, but really it was vulnerable to this coordinated troll attack. So hundreds of users identified a way to interact with Tay in order to change the language and structures that the chatbot was using in a way that was not anticipated. Okay, so how do these systems work? I can't describe them in a simple game tree representation for you. So they're much more complicated architectures that have a lot of components, but the main components are that a user has a message, either typed in or verbally said. There's some sort of speech recognition and natural language processing that tries to understand the context and the intent and the task that the user is trying to achieve. And this goes into some sort of dialogue management system, which has all the guts of the natural language processing and response generation. And there's 2 basic ways that methods have tried to figure out how to generate responses. The older method is a rule-based matching sort of system that takes some words from the input and tries to match them to certain kinds of templates of the types of response that they should generate, and then goes to a database of responses and figures out how to generate those and sends it back to the user. The more current methods are retrieval-based methods that are based on what happens in information retrieval systems that are used at Google and Bing to identify which documents to return for your queries. They take the same basic technology and take the input as information need and use language models and the contextual cues to match it to some database of responses and figure out from the relevant responses how to decide what to return to the user. So what's the complexity in how to develop these dialogue systems? The two major dimensions of complexity that contrast with the game playing systems are that although language has structure and rules like games, it's not as clear-cut as the actions and the outcomes in games. So for one reason, it's continually evolving, so words are being added to our language all the time. Rules are broken, the way people speak, they don't necessarily follow those rules, they invent slang, there's colloquial terms, there's the use of sarcasm and irony and humor in ways that we use words in which they were not intended. And so this means that the search space for what these algorithms have to consider and how they learn how to behave with this user input is effectively unbounded. So there are an infinite number of possible scenarios that the user can be put in, and you have to develop a scenario, a system that's going to be robust and able to adapt to scenarios that they haven't seen before. The second type of issue is that the feedback about whether you're doing something correct is much more vague and unclear. So, and you would know that from your own social interactions and how you try to interpret who's happy with you, who's not, who likes you, who doesn't. The feedback is often unclear, and often there's a much longer delay before you get such feedback. And so you can see this as an issue in terms of what we put as objective functions into our systems. Right now, they would be trying to optimize something like the length of conversations that people have with the chatbots in order to use that as a proxy for something like satisfaction or user engagement. So what does Tay do as a system? So again, just like with AlphaGo, it's using deep learning. I guess I should say that the Microsoft people have not written papers that have been published in Nature describing the entire system. So the information that I have here is gleaned from many talks that I've seen from people at Microsoft Research about other component technologies that they're developing, as well as some of the information that's been discussed about Tay. It's pretty clear that they're using very complex natural language processing that is based on deep learning techniques as well. And so what they've really done is move beyond these simple matching and retrieval-based systems to use complicated deep learning models to predict what kind of responses are likely to be a good match to particular user inputs. And again, they're using massive amounts of training data, just like the AlphaGo system. So they're using millions of examples of interactions between users that they get from Twitter or other kinds of online sources where you can see these kind of engagements over time. But the big difference here is that in this chatbot system, it's really what I would call an open system versus a closed system. There is no clear bounds to the types of interactions that they might have, the types of behaviors they might see from people. And this makes it very vulnerable to attack. So, for example, they never anticipated that this kind of coordinated trolling attack would happen when they were developing the system. Okay, so the dimensions of complexity here with respect to dialogue systems are similar to the things that we talked about with games. And in this case, now we have a third size of space here, which is an open system or an unbounded search space. And now we have feedback that is not just even just delayed, but it's vague or it's unclear. And so we see as we go on in the world, in the development of AI, we tackle harder and harder problems with these systems. So when we compare the two, the game playing systems and the chatbots, we can see that when the problem can be formulated with clear, immediate feedback in a tractable search space, then we're able to solve it pretty easily. And so those are really the situations where it's considered easy, and we have our major successes in the community. But as we go further up to this upper right-hand corner, that's where our problems are still hard and really where the current work needs to happen. So if we go back to discussing the difference between AlphaGo and Tay. So both, when I said that they were built on the same underlying technologies, really that's that they both use deep learning methods that have shown a very significant and impressive improvements in some areas of machine learning lately, as long as they have massive amounts of data from which to train them on. But one major difference between what AlphaGo did and what Tay could do is that Tay can't learn from playing against herself, which is what AlphaGo did. So in the AlphaGo system, because the rules of the game are very clear and whether you win or lose is very clear, they could take different versions of their system and play them against each other to generate even more experience of the different types of sequences of moves and outcomes that you would see. But that's impossible to do with Tay, or you could do it, but it wouldn't be successful to make the system robust to the kinds of interactions that you would get in the real world with real users, because of the variety of kinds of behaviors you would see from users. And so what Tay needs to do to get the kind of feedback and experience that AlphaGo is getting, Tay needs to be out in the real world interacting with users and using that to figure out how to behave. And so that meant when Tay was released onto Twitter, she was still learning. And so what happened with this coordinated troll attack was that users created conversations with Tay and used language in a particular way that eventually made Tay think, this is how people talk, and this is what I should say. And so eventually, after enough interactions with these kind of people, she was turned into a horrible person. And what I like to explain, as an example to explain this to students, is that if you can think of, although Tay was very successful as an algorithm and had learned a lot of things about interacting with humans, you might think that her amount of knowledge would be equivalent to a 7 or 8-year-old child who had had some experience with interactions with people in a very limited environment. And you don't let a 7 or 8-year-old child out on Twitter, right, to interact with the general public on Twitter. And so the difference when Zhao Ice was operational in China is that in China there's a lot more restrictions on what kinds of information is on the internet because of the cultural control. And so they don't get really the same kind of interactions as you might on Twitter. And so if you think about this, you might say, as I did from an algorithmic perspective, we should have known that this could happen, and the algorithm should have been able to detect that people were specifically changing their behavior and how they talked in order to make this chatbot behave differently because of the adversarial setting where they know that they can change the input in a way to change the output in a terrible way. But this is very complicated to detect algorithmically because it's very easy to say in hindsight that there are hundreds of people that participated in this coordinated attack. But when it started, it was very subtle, and it's very hard to detect and know that one individual interaction is not a valid one, that it's an adversarial one. And so it's difficult to encode that in a program to figure out how to identify it and adapt. And this is why when we have our young children and we're teaching them how to interact with people, we don't let them go on Twitter right away. We could send them to kindergarten and they interact in a very constrained environment with people who are kind and loving to them. And maybe there's some bullies in the class, but eventually they have only just small doses of it until they figure out how to interact in those situations. So in terms of what we need now for future research, really what we have to think about is that we have to push in this direction where we're moving to unbounded kind of situations where we're going to have our systems behave. And this is something that humans are able to do very easily. well, maybe not very easily. Some people are able to do them very easily, but we expect people to be able to adapt to new situations and learn how to behave with relatively few examples as they have, after they have developed over time into an adult. And so the way that Microsoft is trying to encode this information in their chatbot system is that they're working with improv actors. And so this might be surprising to you that this is something very non-computer sciencey, right? That they found that what do improv actors have to figure out how to do? They're thrown into new situations all the time, and they have to figure out how to keep the act going, right? Which is exactly what they want to do with chatbots. And so this is something that they're working with humans who seem to have the skill to figure out how to algorithmatize that ability. And then maybe if we learn more from how they view their interactions, we'll be able to put that into our algorithms easily to deal with this open-ended system. The second issue is with the dimension here of feedback. And so we really have to figure out how to deal with this subtle, inconsistent, maybe long-delayed feedback. But that's also something that we do fairly well. Maybe people with emotional intelligence do it better than others, but that's something that we can figure out how to do ourselves. So it should be something that we can figure out how to do in the algorithms. And so the new areas of computational social science or computational humor are the kinds of research directions that are trying to take these into account. So computational social science is really nominally the area that I'm in when I try to come up with machine learning algorithms that will take into account interactions between users. Really what I want to move to are complicated situations where many people are interacting with many other people, and we'd like to learn how to predict their behavior in those situations, but it's not as fixed an environment as a game playing system where you have continual one-on-one interactions over time. People interact with different sets of people and then move and change groups and things like that. So the ideas from social science of interpersonal communication, impression management, ostracism, all of these kinds of ideas need to be put into our algorithms and our learning methods. Computational humor is another area where we're going to have at least a few speakers later on in this conference, including Bob Mankoff this afternoon, talking about how do we understand what's funny, how do we know what's funny, and how do we put that into, how might we put that into an algorithm is another interesting direction to try to deal with the situations where there's not clear feedback. Okay, so to wrap this up, we've made really great progress in AI over the last 60 years. We have things now that are starting to become reality where we have self-driving cars that are able to automatically identify what they see from sensors and figure out how to adjust the car as it's driving. We have smart buildings that are able to automatically adjust temperatures and airflows based on optimizing energy consumption. And we have the beginnings of personalized medicine where instead of deciding one treatment plan for large populations, subpopulations of the general public, we're starting to have methods that are being personalized to someone's genome or their history of illnesses over time. And so this is really an exciting time for this field so computer science in general, AI and machine learning specifically. And so you might be tempted to say, oh, well, these dimensions of complexity that I talked about, it's not too hard. We will eventually go into that upper right-hand corner without much effort. But I would caution you here that as a community, we've always notoriously underestimated the difficulty of the problems that we're addressing. And so what I'll end with here is this, this story that all AI students know about, but you might not know about. So in 1966, so 10 years after the beginning of AI, Seymour Papert, who was one of this group of MIT faculty that really started the field, told his graduate students to solve the computer vision problem as a summer project. And why did he think that they could solve it over the summer? They said because unlike many other problems in AI, computer vision was easy. because it was clear what we were trying to solve, and it was easy to encode that algorithmically. And so now, 50 years later, we're still working on this problem. That was supposed to be a summer project. And so, but maybe we're close to solving computer vision fairly soon, based on all the work going on in AI. This is, so I'll close here with this image from the Facebook's vision system, which is able to take images that are uploaded on Facebook, and it can automatically identify components of the image and know what they are, so it can produce a textual representation of what's in the image, and that can be used to produce a verbal description for blind people. And so this shows you the capabilities that we have with our systems now in terms of how much can be identified. So from this image here, these are going to be identified as sheep. So all the little blobs are surrounding the objects in the image. And not only can we identify and segment the image and identify the important components, we can also decide what those things are and produce labels for them so that the image can be described to people who can't see it. And obviously, we can use that information for many other aspects of the Facebook system, but the benefit to larger society is clear from this. So I will stop there. Thank you very much.
Jennifer, that was a great presentation. Jennifer, kindly take some questions from anybody who'd like to ask. Because we're recording the event, I'd ask you to come up like I did to the microphone. We'll go for about until 1:15, okay? Thank you.
Hi, Jennifer.
Hi.
So you mentioned emotional intelligence, and I have heard some scientists talking, specifically this biologist George Church, who fancies himself a futurist and is a futurist. He's mentioned before the idea of trying to teach AI emotional intelligence, and it seems like if we could have taught Tay to have morality or a sense of emotion, that maybe she wouldn't have fallen into the trap that she would have fallen into. And I wonder, is there a way to pre-program morality, or is that itself something that we so don't understand that we can't do that?
Yeah, that's a very good question. I think that issue of morality also comes into play when you think about the self-driving cars and the current requirements on how safe the self-driving cars will have to be before they're allowed on the road is a threshold of safety that we as humans can't even meet, because somehow we think that the system has to be much, much safer. We can't possibly release a system out in the world that we think will eventually end up killing someone, even though we as systems might go out and get into a car accident and have somebody die, right? So I think the complexity in that, absolutely there are people that are thinking about how to algorithmatize that, and I think it's likely that we can, but we have to think very differently about it than we would with the game playing systems. I think with game playing systems, everybody agrees on which outcomes are good and which outcomes are bad, because you've either won or lost. And when you think of the supervised learning systems that we develop to predict credit card fraud or to detect spam in your email, there is still a fairly clear signal as to whether a transaction is spam or fraudulent. But when it comes to something as complex as morality, we don't even all agree on what the answer is. And so that is something that probabilistically we could encode very easily if we were willing to be satisfied with that kind of encoding. So if you somehow decided on how to value human life and what kind of action you would take if you were about to get into a car wreck with, say, 10 people in front of you, if you're driving, you would get into a car wreck and possibly kill 10 people, or there's one person on the side of the road, but it's your grandmother, what would you decide to do? We would all make different decisions, and if we could answer what decision we would make, we'd probably like to think that, that we don't want to come up with the answer, but we could look at a distribution of what humans would find acceptable, and then probabilistically we could put that into algorithms. But we have to think a lot more carefully about acquiring that feedback and encoding it in order to use it. So I think it will come, but I think there's going to be some tough philosophical discussions amongst us as humans as to how do we actually value these things. Because what the algorithms are doing is they're simply valuing different kinds of outcomes. And so once you put a value on things, we can optimize for it. So if you as a general public can value human life, then we can start developing systems to optimize it. So,
okay. So various points in your talk, the ideas came to me of the possibility of probability of things like computational propaganda and computational surveillance. So I wonder if you'd comment on that.
Absolutely, yeah. So that's those are two good issues to bring up. So computational propaganda would be the situation where we would inject bots into the world that would try to persuade people to do what we wanted them to, pretending to be, just regular people, just like the way humans would try to propagate that propaganda. Trying to be robust to that or detect that is as difficult as detecting the troll attack, because we really have to understand what's valid behavior, what's propaganda, and the line between what's valid and what's propaganda is very tricky to define, because I could be trying to persuade someone to vote for a particular person in the election, but I wouldn't necessarily think of that as propaganda. But eventually, if I try